Right?
During lab time slot.
We need to go.
We're gonna go over to SAS right after this.
Will I be in the classroom even though it's very loud?
Unless you want to take it in the hallway. No, we'll either come over here or I'll find a small classroom we can use.
I see.
Yeah, the lab is on, although we can bring in one of these chairs over there and sit over by the computers. So you're at a normal height too, if everything is full.
Okay.
Look. Did I show you all? I figured out how to set the presets over here so I don't have to fiddle with it. You just do that. It zooms right in. I appreciate that. It's consistent at least.
Yeah.
There we go. All right, and I thought also we didn't have any quiz questions this weekend, obviously. Luckily, the Canvas thing got resolved quickly, so we didn't have to. And
Yeah.
we're an in-person class anyway. They were very. I had an 8 a.m. meeting on Friday with the admin who were panicking about what were we going to do for the online classes.
Yeah.
So luckily that didn't turn into be a whole big deal. But it could have. The IT director was preparing us for it might be several weeks before this is fully resolved. Which, yeah, because they really didn't know, Canvas being a private company, they weren't making it obvious or providing evidence that it had been secured. They were just saying it's up now, but without any reassurances. And so they weren't going to let us get back in and expose the entire system to whatever was going on. So that was its own thing. But I thought about what we were talking about computers last week and how we didn't used to have search functions. And you asked me how we used to find stuff in computers. You can still do that on modern computer if you use what's called the command line or terminal. If you just open up the menu and type in terminal, you get something that looks like this. This is the original, not the original, but the original computers used punch cards. You literally had stacks of paper that you would hole punch in the right spot, and the computer would physically have little fingers drag across and find the holes, and that's how you program things. And so you can actually see there's a video, I think it's Grace, no, not Grace Hopper, I can't remember that woman's name, but the director of the calculations for the Apollo 11 mission that landed on the moon. She had a stack of punch cards taller than she was. It was the programming for landing on the moon. So I'm not that old, but when I first started learning computers, you had something like this. We're talking about when I was like 6. I remember getting my first personal computer at home for the family, but just barely. And to do anything, you had to just type stuff in. So if you wanted to try and find a file, you would have to do things like type in command like dir was list everything that's in this folder. And it would give you a list of contact, whatever is in that folder. If you want to change folders, you would have to change directory / and then type users, except I didn't type it right. Oh, it's because I backslash instead of forward. So if you wanted to go all the way to the baseline, you would do that and say, okay, well, what's everything that's on here? And we get a new list. And you say, okay, I want to look at what's in program files. So you can hit CD/program. Is there space in program files? Yeah. Although I'm not sure. You didn't used to be able to put spaces in, so I'm not sure if it'll actually work. It doesn't like the space. Yeah, or you use dots or underscore. That's actually the use of an underscore. Was a space character because it couldn't handle spaces. because a space was how you signified that there was a new command coming after that, or an option or something like that. So yeah, you would actually have to go click around, or not click around, type around, find files. And then even once you had a GUI, like a mouse where you can actually visualize things, you would still have to go, there was still no search function. You would have to click around like, okay, I want to see what's in program files. You'd go look at what's in program files. Hey, there's this program I've never heard of before. What does that do? So my generation learned a lot from just like screwing around because we didn't have the internet. We didn't have anything else to do. If you wanted to play around on a computer, you had to figure it out yourself, or you had to read a manual. Like I spent a lot of time reading manuals of like, oh, okay, here's a new Windows operating system. How do I do the things I used to know how to do? And you couldn't just look it up in online. You had a 3-inch thick telephone book. You don't even know what a telephone book was. Okay. But they looked like telephone books. That was just like, here's a list of all the things that you can do in this operating system, and here's how you do it. It was not the most efficient way, but it meant that you had to learn what you were doing pretty well. So that's just a historical note. You can still do all of that, obviously. Things have changed a lot. The commands have changed, and I haven't done that in at least 10 years. But that's how we would have to submit our jobs when I was in grad school, because the supercomputer that we built ran on Linux and used a command line. So you actually had to open up a command line, submit your jobs that way, instead of just uploading and hitting run. It was really a lot more work in my advisor's day, because he would actually go to a computer lab in the middle of the night when nobody was there. And he would start, and he would have all of his jobs ready to run on a floppy disk. Okay. And he would put a floppy disk into the computer. He would have 20 floppy disks that were all the same. And he would put a floppy disk into computer 1, run a job. While that was running, he would go to computer 2, put in a floppy disk, run job number 2. And then by the time he got to the end of the row, he would go back to the beginning and check if they were done. So that was really a lot of work. Yeah. We've come a long way since then, for sure. Right. So nobody else would be there. Otherwise, he'd get told that he had to share. Well, this was at Caltech too, and they feel very strongly about you need to be productive, and he was an interesting person. All right, let's do some review of acidity. Let's look at A. We're just going to rank these compounds in terms of increasing acidity. Let's start by drawing them out, and then comparing and seeing which one we think is going to be most acidic or least acidic. Man, somebody else is using my good pens. I'll blame Bruce. It's always safe to blame Bruce. Dichlorobutyric acid. So butyric acid is a common name, but it's close to know, right? Perfect. So there's butyric acid. Three compounds looking at 2,4-dichloro. Or 2,3-dichloro. Or 3,4-dimethyl. That's a typo. What's the typo?
They can't.
Yeah. Because 3,4-dimethyl butyric acid is really just pentanoic acid. So what is it that's going to control how acidic a compound is? They're all acid groups. So at least we're all looking at the same functional group. What holds that H plus on? Why is the H plus stuck there in the first place?
On the OH?
Yeah, why? Why is it attached at all? Let's go way back. What causes covalent bonds?
It's like very beginning first. That's like Gen.
That's Gen Chem. First quarter of Gen Chem even.
Wait. Why is the table like it is on?
Except that now your longest continuous carbon chain is 5, not 4. Not when you put nonmetals with other nonmetals, they make covalent bonds, right?
Yes.
Why do they do that? What are all the elements trying to do that causes them to make bonds? You kind of, because ionic compounds don't mind having charges.
It's true.
So what is it about, if I have just 2 hydrogen atoms, they're going to form a covalent bond. Why? Ionic bonds are actually stronger than covalent bonds. Because they're trying to fill their valences, right?
Yes.
They need electrons to fill their valences. Right, so when you put non-metals together, they're going to try to fill their valences as best they can. So that way everything is stable, right? So what is it that's causing this hydrogen to stick to that oxygen? The oxygen, if we didn't have that bond at all,
Yeah.
we'd either have a lone pair or we'd have an incomplete valence, right? So if it was neutral, we would have this. That's not really what happens though, right?
Right.
It really behaves more like this.
Yeah.
So what is it that holds the H plus on?
The electron?
Yeah.
Oh, okay.
This has a negative charge, this has a positive charge, they're gonna try and stick together because that's gonna then fill the hydrogen valence too.
Yeah.
So what's going to change that causes a difference in acidity between these? The electron density. So more electron density is going to make the hydrogen stick on better or weaker? Is it going to make that oxygen hydrogen one stronger if you have more electron density or weaker?
I feel like the stronger is trying to kick on. Right, like if it wants more electrons.
The oxygen wants more. Right now, everything's got a covalence, right?
Yeah.
If you started pulling more electron density this way, there's less of a force holding this hydrogen there, so there's less electrons for it to stick to.
So the more density makes a hydrogen stick on.
Yes. That's why we started all the way at the beginning. So I'm trying to make this make sense. Right? Because it is a tricky kind of concept. More electron density, just sheerly in terms of charges. More electron density means an H plus is going to stick to it stronger. More strongly. The grammar there is weird, but you hear what I'm saying, right?
Yes.
So, out of these, which one has the most electron density on that oxygen? Are the chlorines going to give electron density or take it away? Why? Because it's chlorine. And chlorine is more. There it is. More electronegative stuff is going to pull electrons away.
So the last one.
So the last one is going to be the strongest. It's going to be the hardest to pull off the hydrogen, which makes it the most acidic or the least acidic. So what is an acid?
That's what I was asking you.
So
Oh, I am.
okay, I see what you're saying. So more H plus is floating around means the solution is more acidic.
Yeah,
An acid is something that gives away an H plus though.
perfect.
So if this one has the most electron density, that means it's the least acidic. So then out of these two,
The,
which one is going to pull the electrons away from the oxygen more?
is the second one.
Because the second chlorine is closer. So if this one has pulling the most electron density away, that makes it the most acidic. And then by process of elimination.
Yep.
Middle. And so acidity always comes back to electron density. The other possible variable is resonance.
Yeah,
Because that's the other thing that's going to make it more stable in its conjugate base form is if we get extra resonance structures. So we look at benzoic acid versus cyclohexanoic acid.
the benzoic is more acidic because it has more resonance.
Because once we pull that hydrogen off, it's going to be more acidic. The other way you can think about it is conjugated bonds with electron withdrawing. Okay, so that then follows our same logic.
Yeah,
But the way it's presented in a lot of textbooks is, oh, you just look at the conjugate base. This conjugate base has a lot of ways it can resonate that negative charge rounds.
Yeah.
Which is another way of saying we're pulling electron density away because we can share it in lots of different places. So more conjugated bonds is going to make something more acidic as well. And in general, this is a sort of a sliding scale. I don't like to make sweeping absolutes. But in general, resonance matters more than
right,
induction. This is pulling electron density away through induction just by sheer electronegativity. Mostly resonance matters more. There are a few extreme cases, like you had trifluoroacetic acid. That I believe trifluoroacetic acid is more acidic than benzoic acid, even though it doesn't have resonance structures. But I'm gonna try not to ask you any of the gray area. It'll, in general, when I'm probably gonna ask you two of these questions on the test. One of which is gonna be like this first one, where all you're doing is looking at electronegativity. And the other one is gonna be resonance based. I might throw a wrench in things by saying, okay, your third one is benzoic acid.
that one's gonna be more acidic because it has the bonds and.
So if I'm asking about something where both the resonance and the induction is changing, I'm trying to make it so that they're working together, not so that there's one that's sort of right. I wouldn't ask you about this one.
Okay.
Because that's true. That's now asking you to evaluate which of these is more important, the resonance or the fluorine.
Yeah,
And that's one that I don't expect you to have memorized at this level.
Okay.
I'm not sure I could answer. I bet if you put a fluorine here, it's gonna be pretty close. And I bet if you put two fluorines on, it's gonna be really close. But I'm guessing at this
Yeah,
point,
yeah.
so I won't expect you to do that on the test.
cool. Should we do the B?
Let's do B.
I wrote that these words are so long, I missed dashes. Bromo for a world beyond. What is like ionic as an ending? Hold on.
It's still an acid and it still starts with pro. So propanoic would be the IU.
Oh.
So it's similar to butyric. Butyric is a common name of the IU. I think it's close enough. We're just gonna. Don't second guess it.
Oh, and then. I'm gonna do my perfect one. Yeah.
Hoping it was gonna be cold.
Yeah.
I'd always rather have it be cold in the classroom than hot.
Yeah, I agree. I get really annoyed when it's cold, but it makes me tired. And it's just-
I would say I've had the opposite.
I know.
When it's
most people
warm.
find opposite.
I have students dozing off, like this time of year when I'm upstairs, that big classroom. Everybody's sleepy after break.
Oh, wait, no wind. Oh, it's just flipped. It's not.
Because I count my carbons first, and then that's when my pen is, so that's where I put the functional group.
Because it doesn't matter, we're the same thing. Wait, I have this stuff. That's the electron density. So then it will be with the opposite. But I kind of looked up like the Phoenix chemistry graph patterns. So there wasn't a lot of ones. But I found one that was like my sponsors and then I listed formulas for caffeine and ethanol. And I thought that was pretty, but I don't think a lot of either of those, so it doesn't sense for me.
That's doubly funny because sponsor can also be somebody who's helping me with.
Oh, yes.
Okay.
I know, I thought it was funny, but I'm trying to come up with what to do better.
All right, so what's gonna be? So when I've got three that I want to rank,
Yes.
I usually find it easier to put them into pairs because usually there's one thing I say is gonna be,
Like more than that.
yeah, okay, what's changing? So out of these two, it's pretty easy to see, right?
Yeah, we have two over one.
So
It has more electron density, so it's less acidic.
this one is least less acidic.
What?
Because it has more, you have bromine's electronegative, right?
Yeah.
So only one bromine means it's pulling on the electron density less.
Right.
So that means the OH has more electron density, which makes it less acidic.
Oh boy, okay, so maybe I have to write first. Then like the farther and less stuff away from the OH, this acidic.
Yes.
So the less, but I thought the more electron density makes it more acidic. Oh,
Opposite, because electron density is what's holding that H plus on. So the more you pull electron density away from the acid group,
very good. I'm just confused. It's okay. I'll get it. It's just a little turnaround.
You had it once, so just let it marinate.
Yeah.
So out of these, the bottom one is more acidic.
Which,
Out of this one,
which two are we looking at?
the top and the bottom.
Okay.
Out of the middle in the bottom, they both have two bromines. These ones are closer. So if this one's more acidic than the bottom, and the bottom is more acidic than the top, there's our order. Most acidic, mid, least. And also, if you don't have to use numbers to write things, don't use numbers because that's confusing. Easy to mix yourself up. Just write the words most acidic, least acidic. And then it doesn't matter 1, 2, 3.
So I'm assuming we're dealing with a lot of this that is hidden.
We're because we didn't do the, I didn't send you practice problems over the weekend. I wanted to spend a little bit of time on, since this is one of the trickier concepts we had on Thursday. We are actually not going to be dealing a ton with acidity today. We're going to be dealing with acid derivatives, which are 4 more functional groups. So we get to learn how to name. So these are our acid derivatives. They all have the same oxidation state on the carbon as an acid. The other one we can include in here is a nitrile. Which would look like this. It looks substantially different, even though it's still same oxidation state because we get an sp1 carbon instead of the rest of these are all sp2 carbons. So depending on whether you're using the hybridization or the oxidation state, you might. Well, I guess the other reason this isn't always included in the same group is the rest of these have a good leading group attached to the carbonate. This one isn't a carbonyl at all, and it doesn't have a good leading. So even though it's the same oxidation state, we can convert back and forth between this and the others relatively easily. It's not typically considered an acid derivative. I just wanted to remind you that they exist.
It was part of our, like, agents.
Yes, exactly. That was one of our easy ways to make a carboxylic acid is to use a cyanide group as a nucleophile and then oxidize or not oxidize it and then change it from a cyanide group to an acid group. That was one of the reactions we added last Thursday. All right, so one of the things that the other reason these all get lumped together along with acids is that we can pretty easily convert between any of these. Yeah, we can go from an acid halide to an amide, from an amide to an ester, from an ester to an acid to an acid to an acid hydride. Pretty much it will. It's not going to be perfect yields, but it's a pretty straightforward process. All right, so that's why we take them all as one group, basically, is because it's easy enough to move them back and forth. So acid halide. We just replace the OH with the chlorate, or with, you can have to do a bromide as well. Maybe even an iodide, but chloride is most common. Acid anhydride is just two acid molecules stuck together. So instead of having an OH, you added a whole nother carbonyl to it. An ester is like an ether that's also a carbonyl. And it's the similarities in the naming. It's an acid ether ester.
This is or with the injectables, ether, ester, and anhydride, are they all the same, just one step farther to reach?
Yeah, bingo. And then an amide, we have to be careful with amides because organic amides are a functional group. But if you just say sodium amide, amide is also a polyatomic ion. It's the conjugate base of ammonia. So NH2 with a negative charge is also called amide. So you just kind of have to know from context, are we talking about amide as functional group or amide as nucleophile or base?
And they came back and forth between any of the four plus acid.
Yes. And I suppose one more for the, if we had the deprotonated, so this is a carboxylic acid. I always want to put two L's there, but I don't think there are two L's. If that's a carboxylic acid, the deprotonated version of the carboxylic acid also has a name as well. Remember your classic inorganic acid nomenclature from Gen Chem, like nitrate as an acid, it's nitric acid, right? So carboxylic acid, when it's deprotonated, we just switched it back to being the 8th form. So a deprotonated carboxylic acid is a carboxylate. Right, it's the same base. So just like acetic acid, when it's deprotonated, is acetate. Benzoic acid, when it's deprotonated, is benzoate. So carboxylate. Right, so these are really the same molecule, just the conjugate base form, but they do get named differently sometimes. And that's going to show up. Turns out that's also going to be how we're making name esters. Esters are the trickiest functional group to name, period. Because they are. At least me. We'll find out, yeah. All right, and then here's nitrile, not as easily converted to other groups, and they don't have a good leaving group, but they have the same oxidation state. These typically, we're just going to name these, unless that's really the only functional group, we're just going to name it with a prefix. This branch has a prefix of same.
Okay.
So if we had this, this is going to have a name something nitrile, ethyl propyl nitrile or something like that. You could also just call it 3-cyanopentane.
So we don't have to include it if you want.
For this one. Like I said, nitriles don't show up as much as the other ones, and they typically get named as a branch anyway, because this whole thing is a good leaving group. And can get replaced through an SN2. All right, so let's just go from left to right in terms of naming these. They're all going to follow our normal structure. Find your longest continuous carbon chain that has the acid group, the acid pyrimidine group.
So we're like ID packaging them?
Mm-hmm.
Are we just gonna say R is, oh,
We basically, if you name it as the acid and then adjust the names, is the easiest way to think about it. So like, this is acetic acid, that's the common name, not the IUPAC name. But either way, if it's the acid bromide version, you just drop the ic acid and you add YL and then whatever the halide. Which makes them sound funny sometimes. So acetic acid becomes acetyl bromide or chloride or whatever.
Right.
Benzoic acid becomes benzoyl chloride.
Okay.
I did have the nitrile nomenclature up here. The other way of doing it is just put nitrile at the end.
Right.
But either way, you name it like it's the acid, and you're tweaking the ending. Anhydrides literally just say anhydride instead of acid.
Okay.
As long as it's symmetrical. Typically the most common anhydrides that you're going to see, it's going to be the same acid group on either side. So you just name it like the two of those stuck together. Acetic acid becomes acetic anhydride. Occasionally, some of these dioic acids, they can make a ring closing.
Okay.
So succinic acid becomes succinic anhydride. It's not two succinic acids stuck together, it's succinic acid stuck to itself. That's sort of that's the more rare case. Dioic acids are not as common. And you have to be able to make, it has to be at least this big in order to make a 5-sided ring. So like oxalic acid. The IUPAC name would have been ethane dioic acid. You can't do that. Because if we took away, we basically are subtracting a water. It's a dehydration reaction to make these. So if we did that, we'd wind up like a 3-sided ring. Like that, right? That's not safe. Yeah, it does look like a mouse.
The acetic anhydride, if they add an OH on both ends, would we prioritize the anhydride name or would we prioritize like diacetic acid with the oxygen? Or does it matter?
So typically, if you have those kind of questions, go to the back of the textbook in that appendix that has them listed out in terms of priority. But in general, whatever we've covered most recently is the higher priority. Kind of go from the lowest priority and start going up the ladder of complexity. So the ones we've done most recently usually take priority.
Okay, so yeah.
So I think we had an OH there.
And on the other side. Yeah. It'd be like.
That'd be hydroxy acetic anhydride.
Okay.
The other way that you can go about it is if you know what the prefix is version of it, like we know how to name that as alcohol, but we also know it could be hydroxy.
Yeah.
We don't know what this is as a prefix. So name it the way that you know how to name it.
Yeah.
Because really what's most important, what's even more important than that priority table that I keep bringing up is the fact that the name is unambiguous. So if you know how to name it unambiguously one way, even if it's not technically correct, as long as somebody could read what you wrote and get the right structure, that's more important than getting the priority right.
But it wouldn't be acetic anhydride.
Diol.
Yeah.
No.
Okay.
If it's not a symmetric anhydride. you just name both of them separately. You just say what's on both sides of the anhydride. It's acetic acid on this side, and it's benzoic acid on this side. So it's acetic benzoic anhydride. And here's where we want to be careful. This is also where the esters are going to trip you up. You'll notice this is one of the first times we're actually making these things two separate words. It's not acetic benzoic one word. It's acetic space benzoic anhydride. That means you're naming both sides separately. If there was anything attached to the acetic acid, it would be named all as one word over here, right? Like if we had a fluorine on this side, you'd say fluoroacetic benzoic anhydride, but we need to make sure that the space stayed there. The same if we wanted to do it, if we had a fluorine here. I'm not getting sick, this is just allergies.
I think I was just having a like. Then I lost.
When you have small kids, it's never just allergies. And you work with small kids. So if we had something like this, we have fluoroacetic fluorobenzoic. We wouldn't say difluoro because we need one of the fluorines on each side. So then we would still use our numbers, like, okay, we don't need a number on fluoroacetic, it's only one place it could be, but we could say 2-fluorobenzoic. We already made 6. All right, we're going to power through these and then we're going to do practice with them. So amines. Again, name it like it's the acid. Drop the acid and just say amine. So acetic acid is acetamide. Benzoic acid becomes benzamide. If we ever have something attached to the nitrogen in an amide, and we need to name it. So this would be our primary functional group here. Or our primary parent molecule. So we name it acetamide, and it has 2 methyls attached. And we need to specify where they're attached. So this is why we don't just call them numbering the carbons, because there's cases where we're not numbering a carbon, we're specifying an atom that's not a carbon. So that's why we call it locants. A locant, like location. The locant N means it's attached to a nitrogen. So N dimethyl acetamide means acetamide with 2 methyl groups both attached to a nitrogen.
If you had 2 nitrogens, would you number them in the same direction as the carbons?
Typically, now we're getting into where there's usually a common numbering system. I've seen it, it's N prime,
Okay.
where you use apostrophe to indicate prime. How do you know which one is N, which one's N prime? Usually it's because you're starting from a common molecule that's already a convention in place. So that'd be a case where you would look it up.
Okay.
Or if it's symmetrical. So let's say I made it tricky. I didn't mean to do that. But just as far as these nitrogens are symmetrical,
Yeah.
So it doesn't matter which one's N and which one's N prime. So you just say N prime, because it could also be that, which would be N dimethyl versus N prime dimethyl.
Yeah.
But to go back to the original way you framed that question, I have seen cases where it's N1 and N2, where they number them instead. If they're not symmetrical, that's probably what you do, and you probably just make it match with, keep the numbers as low as possible, the way we approach that. All right. Esters, the tricky ones. So you name it like it's the acid, and then you say what's on the other side of the acid. But it's not an acid anymore, it's the protein. So we name it as the 8, the carboxylate version. So acetic acid would look like this. When you take the hydrogen off, it becomes acetate. And then whatever you add to the other side, we specify as a separate word with a space in between. Right, so that's how we distinguish between a branch that's on one side versus what's on the other side of the oxygen. It's an ethyl group attached to acetate. So again, if there was a fluorine attached here, it would be ethyl space fluoroacetic acid or fluoroacetate. Keep the space there so that you're not saying you're otherwise, if you run all this together or even put a hyphen there, you're saying that the ethyl is attached to the acetate side.
Okay.
The space is what indicates that that's on the other side of the oxygen.
Yeah.
Which gets really tricky when you're saying it verbally. There's not a way to say it verbally other than saying space
Right.
or writing it out.
Why don't we use like capital letters to distinguish the space?
Because chemicals are not proper nouns. And elements are not proper nouns. So that goes back to our rules of English grammar. When it gets really frustrating because if you have, say, Mendeleev, the guy who invented the periodic table, you capitalize that. But you don't capitalize Mendeleevium. I lost a syllable in there. So even if it's an element that's named after a proper noun, once it's the element, it's not a proper noun. So like Curie and Curium. Curium is named after Marie Curie, but you don't capitalize Curium.
Okay. But when we when we use capital letters, when we put them into the structure,
Only
the first,
if it's the first word in a sentence. Oh, or do you mean when I like this?
yeah.
Because those are not the names, that's the atomic symbol. Atomic symbols have to be capitalized properly, but the names are not proper nouns. I like that you're thinking about all these details because these are things that I think about too.
Well, it's kind of, but it's
It's a little bit. And again, it's a really common mistake, but as long as we're splitting hairs, that's why we don't just capitalize it. It's because to be most correct, if you wrote it as ethyl and fluoro, and you capitalize both of those,
yeah.
Like I'm not going to mark you down. Nobody's going to get confused about what you're saying, but it's not technically correct grammar if you're trying to put that into a sentence. Chemicals are not people too.
Are we supposed to have articles by next week? Oh my god, I forgot about that.
I think that might be the last, but it might be the rest of our labs, because next week 7's lab is gonna be taking the tests. So week 8, 9, 10, and 11, like we might do one more wet chemistry lab. But I think that's gonna be the bulk of what we're doing from here on out, just gonna be working on that, so I'm not too worried about that. Because originally the midterm was in week 6, it made sense to set the deadline in week 7, but now because our midterm's in week 7, we'll talk about it. We'll talk about it on Thursday probably, except that that's senior day
Oh, yeah,
and might be canceling class that day.
yeah, we might
So you can go, so your class for the Thursday after the midterm
be finding.
will be finding the articles. That'll be a collaborative thing too, because you're gonna go out and find a bunch of options, read the abstracts, come meet with me, and then we're gonna sit down and talk, okay, well, this one isn't really relevant, this one is too niche, or it might be, has other concepts we haven't covered yet, this one looks really good. So that'll be where we'll work together on picking the articles. That'll probably be what we do in week 8's lab.
Yeah. And it's.
No, I want you to do them separately. You can work together to try to understand them, talk about them, but I want you to each present your own article. And that's good, because that means you can pick. And you'll be able to pick something that is equestrian related. Synthesis of ketamine for horses. Or the way ketamine is broken down in horse bile. That's the only medication I know that's specific to horses. Because it got its start as a horse tranquilizer. And Riley can do something dental related or pure chemistry or whatever.
No,
Yeah.
Like.
Cosmology.
Yeah.
Well, so cosmology is about the origin of the universe. That's more of a physics thing. But you probably mean like cosmic chemistry or astrochemistry.
But
Yeah.
that might be too broad, like, I don't know. What?
That's a good place to start. And you just start going down the list. Oh, because every paper you find is going to be very, very specific.
Yeah.
You're not going to find a paper like organic chemistry in space.
Yeah. Yeah.
So it's a good place to start. All right, do I have some practice problems on next? We'll do a few of these and then we'll take our break and then we'll do the rest.
Okay. Sorry, I keep getting us on confused.
That's okay, we have time. Let's do A through E on the top. And then we'll do the rest when we come back to break.
Okay. Well, we know that there's a series in anti-drive. Just dying of sleep is it. Here's this one, you want to put on same page, right? That's seated. You just change acid. Yes, but it has extra metals. If it's acidic. And when I drive it on. Dying. Oh. Chops the electronics eating the front. So you can assume that you can figure it out, see that. With this. Well, I should have drawn them off of the letter. This thing and return those cards. How do you say it wrong on the slides? Attached to the on 2 different slides. Yeah. Maybe it says, but we can't say one on top. specify those. Yeah, but they can be on the same side.
So is this symmetrical anhydride?
Yeah.
So you just name it like it's just the acid. The part that I circled would be propanoic acid, right? So because it's the same on both sides, we would just say propanoic anhydride.
Why are we using propano? Why?
Oh, we could use the common name propionic if you want. But because 1, 2, 3 carbons. Our longest continuous carbon chain.
It's anhydride.
Go ahead.
Look at. There's no dashes.
No dashes. This is space.
Oh, okay, no, listen, it's attached to an N. We have NN dibromo, and then we have
Dibromo?
dimethyl.
Diphenyl. Because when we name a benzene ring as a branch, it's a benzene ring.
I thought those only that have carbon.
No, that's even backwards. A benzyl group is if there was a carbon in benzene. It's just the benzene ring directly attached to the phen.
Okay,
Those are more common. A benzyl group is less common.
okay. I don't know, it used to be so fun and easy.
We'll get back to that in a second.
I don't name that. Well, it's about. Well, no, because it has extra carbons too. Okay, wait, so I can make this, and we name this. This. Do you want to say this is? Never mind, but we probably specify which carbons. Well, I turned into. Would be propionate?
Close.
Propionate.
Propanamide. It'd be propanoic acid, right? So we're just dropping the oic acid, so propanamide. If you said propamide though, most people would know what you're talking about, but it's technically you missed the syllable.
Yeah, but it's connected. I'm just gonna try this. Wait, should we put that? There is. Someone who understands. You pay the second one.
Yes. So we know it's propanamide because the side with the carbonyl is our dominant side. Right? That's the side that's going to control the parent molecule.
Yeah.
So it is propanamide.
Okay.
Because it'd be propanoic acid, but we delete the oic acid and just say amide. So propanamide, it's got two phenyl groups, both attached to a nitrogen. So N diphenyl,
There is that.
or you make it the same word,
Okay. No space.
no space. You only use the spaces for esters and asymmetric anhydrides. Okay. If it's an asymmetric anhydride, you say what's on one side and then what's on the other side. As two separate words. But if it's not an anhydride or an ester, it's all one word still.
Esters and asymmetric anhydrides?
Correct. So if it was this, that's propanoic on one side and butanoic on the other side. So that would be propanoic, butanoic anhydride, all the separate words.
But don't we have space here where it's symmetric?
Between propanoic and butanoic. Just like we did that. So yes, I guess you're technically correct. I just mean in between the two groups on each side.
Yeah.
But yes, you're absolutely right. There's a space before anhydride as well.
So only spaces for esters and anhydrides.
And if you want to say for the acids as well.
It's like a trans satellite. No, but it's magical, but they're not on the same place.
Let's skip this one. Those dioic acids all have common names. So don't worry about that one.
That.
So if we're not going to use a common name, but and this is also the way I approach this on a test. Holy crap, we didn't talk about that yet. And it's on the test. Find an example where it's going the other way if you can. Like down here. Dimethyl oxalate, that's two separate words. That's going to be an ester. Where your parent molecule is the oxalate and you've got a methyl on each side. And it's two separate words because the methyls are the other side of the ester group. So that's what we do here. We've got 1, 2, 3, 4. So even it's going to have a common name, but even if we don't know the common name, we could still name that as butane dioate. Because it would be butane dioic acid if it was protonated, right? So butane dioic acid would look like 1, 2, 3, 4. Would look like this.
Okay. Yeah.
To make it an ester, we drop the H from both sides. And now it's not butane dioic acid, it's butane dioate. And then it's in this case, because it's a methyl on both sides, we would say as a separate word, dimethyl. If it wasn't the same group, if it's an ethyl on one side and a methyl on the other, we'd say ethyl space methyl space butane dioate.
So is there a dash for
Space. Because we're saying the ethyl group is over here on the other side of the ester. Space is indicating it's on the other side of the oxygen.
with ethyl?
The way that I drew this one, I added an extra carbon so that it wasn't symmetric. The way this one's drawn, it would just be dimethyl.
Space.
Dimethyl space butane dioate. So name it as the acid. Deprotonate it, so it's 8. and then you say what's on either side. D, we should be able to do that.
Sorry.
You don't use that logic with the amide stuff. The amides, everything's all one. This is why esters are so tricky, is because they're different than the rest of these. Than everything we've done so
Can
far.
I just put dashes instead of
Yes, you can still use the dashes like we've been doing. We just need to make sure that it's not a space.
Yes, dashes like that becomes one word. It is one word in the dash. No, like. That's the same thing. No, because you didn't take it with the equal. Same thing. Oh, it's not the same. What?
So this is one of the ones like, remember carbaldehydes? We had a cyclo group that had an aldehyde attached to it. We said cyclohexane carbaldehyde. Do the same thing here, or you can say carboxy cyclobutane. I would be kind of tempted to just name it as methanoic acid as the base. So I'm starting from the base. Just start as an acid, and then we change it to the amide. Right, so we name it as the acid, and then you drop ic acid, and we write amide. So cyclobutane carboxylamide.
Why do we do the carboxyl?
Because we name it starting as an acid. These are all named starting from the acid name and tweak the acid name.
So like we're replacing the whole N and everything else as just like the OH.
Just OH.
Okay.
That would be cyclobutane carboxylic acid. Then we drop the ic acid and write amide. So it's cyclobutane carboxylamide. And then we say what our branches are. N-ethyl, N-methyl, cyclobutane carboxylamide.
Okay, the only thing I missed is the carboxyl. Well, you also switched, you have the methyl left. That's just alphabetical.
Yeah. Saying methyl for, we're not thinking about that, right?
Right.
About the alphabetization. I think that's a word.
Maybe this is- Or actually, the minute. If there's no. Oh, already. Right. That's how it is. You do a senior dimension. And then you already have a lot. It's not really.
Hmm,
When you see C and then switch other like that, it's always on.
correct. When it's written this way, if there was something else attached to the nitrogen, then we would have a amine, not a, or an imine or something like that instead of a nitrile.
Leave this something.
Correct. So I checked on Molview. Molview does drop the YL as well, so it's carboxamide,
Okay.
but either way, name it as the acid, drop the A acid and write amide instead. For all of these acid derivatives, they're derivative of the acid, so name it as the acid and tweak it.
Okay.
Right, so
No, I don't understand something about it. We did that to regarding level one, like this one is just that we. Which is. There was a level one.
So the big question with this last one, I know we're going right through our normal break time, but we'll take our break, I promise. The big question is, do we name this as a propane or as a butane?
Oh.
Because it looks like 3 carbons and then a nitrile group. But is this carbon count as part of the carbon chain? It is part of our longest continuous carbon chain. So we would name this as butane nitrile.
How would you name it supposed to?
If it didn't have the N, it would just be butane.
Is there before?
So this one's not technically an acid derivative, even though it's the same oxidation. This is the weird one out of the weird one. So we're just gonna name, we're saying nitrile because it's got a nitrogen triple bonded to a carbon.
That's what that means. But you always draw those kind of things. It's don't draw it, it's a single bond and it's physical agents that happens. That's why I'm so good at this. Go right now.
You could also say cyanopropane, 1-cyanopropane. Because the cyano, so if you name it as a cyano group, the carbon does not count as our longest continuous carbon chain. You name it as a nitrile, which is the ion pathway of doing it, the carbon does count.
What if I had to propane site? Does it have to be that order?
Yes, because cyano is a prefix.
Okay.
Or you could say propyl cyanide, but that's the old school way of naming things, and I wouldn't encourage you to do that.
So cyanide itself, is it just a carbon and a nutrient?
Yeah, cyanide, the polyatomic ion. It's just that.
Why is it this?
Because it's the same shape as an oxygen or carbon monoxide. So carbon monoxide looks like this. No, cyanide kills you very quickly.
Maybe dead girl. What's that? The chloroform?
Chloroform. Also very prevalent in old school detective stories, Agatha Christie's and such. Cyanide is the one that will kill you like that. And And chloroform will knock you out and cause brain damage. They just don't. They ignore that part. Everybody always wakes up from being knocked out and they're fine. Chloroform will mess you up for a while.
It's no.
And if it's done repetitively, like to the same detective in multiple stories over and over again, yeah, you're gonna have some long-term issues.
Yeah.
So it kills you because there's a lone pair here
Yeah, that's kind of funny.
and here. So it bonds really, really well to the iron and hemoglobin.
Okay.
Like, I want to say carbon monoxide bonds like something like 200 times, 80 times or 200 times better than oxygen to hemoglobin.
Okay.
So basically it displaces the oxygen and then your hemoglobin, your heart can still pump, you can still be breathing oxygen into your lungs, but it's not attaching to your red blood cells, and therefore your body suffocates.
Okay.
So you're effectively drowning in air so that you can breathe normally.
Right.
This bonds like 10 times better than carbon monoxide. And it's pretty much irreversibly.
Like-
Carbon monoxide is reversible and be fine over time, right? You don't hear about that with cyanide. If you get a low dose of cyanide, they basically need to filter. You have to go through dialysis basically and get blood transfusions. But that's far less common because usually you're just dead. All right, let's take a 10-minute break and then we'll do some more practice and then we'll finish up the reactions and switching back and forth between these on Thursday.
Okay.
Or yes, this week we still have Thursday.
That is the task.
Yes, let's do that.
You coming with right? Maybe.
If you want, you take your break. I'll go find steps.
Okay. I
So. You know, it's all. We don't have.
Basically, about right? She means like, I need to know what to say, or like what not to say, I would be very like. When we introduce you, straight up, so I'm a dentist, I'm doing education, I'm from dental school, I'm going to be speak with my students. And I subject to, I don't know. So it's liberal arts, math and science. Yeah.
But
These is. It's me, Marjorie and Laura. I think I. Oh. This is the birthday girls. I mean, I guess. But I want to get, I want to actually. First.
All right. Let's do a little bit more of this. Maybe we'll even end a few minutes early.
Are we not finishing? So I would that.
Yeah, because that's one of those words with a common name. And I'm not gonna worry about that one right now.
So this would be. Oh, let's do that. Let me do it. And that. So you can put that in there's a new that. And then change the ages to your. That is what I put in my notes. So. No, so we're just gonna look at this, which is just. Giving us. Well, yeah, so then we take the age off. We would say. Wait, so how would you name it? Athlete statements. Or at the last. But that part of it is. Right, we just maybe the original thing. If that's included. Yeah, this is, look, this is the original model. This is. This,
If you're naming it, just the part that I circled that has the acid. It would be butanoic acid.
why is that carbon not included?
It is. 1, 2, 3, 4. But
But isn't it like part of the acid?
no. It's part of the butanoic, if our longest continuous carbon chain that includes the acid group is 1, 2, 3, 4. You with me?
Yeah.
Okay, so 4 means butane.
Yeah.
And then we say, we start writing it as the acid, so butane, drop the E, put oic acid. Except it's an ester, so we're gonna deprotonate the oxygen, so it's not butanoic acid, it's butanoate. And then as a separate word, got 3 carbons. Propyl butanil
Space or dash.
space. Let's reiterate the need for the space there. So let's say we had this. One, two, three, four. So it's still going to be butanoate. Except it's not just butanoate because there's a methyl group attached to the acid molecule. So it's methyl butanoate. And then we need to say what's on the other side of the oxygen as a separate word. So methyl space 2-methyl butanoate. This methyl doesn't get a space because it's part of the parent molecule. This methyl does get a space because it's what's attached to the oxygen.
So it gets a space that is attached to anything that's not a carbon.
Careful because the amides all get jammed together as one word. So this is just think about it for the esters and the anhydrides. the esters and the anhydrides that need to say, okay, what's attached on the primary side versus what's attached on the other side. I warned you that the esters were a pain. I didn't struggle with nomenclature when I was taking this class the first time, except for the esters. I never found any esters. Because they don't make sense compared to our own thing. Let's do H, more practice.
Yeah. Think of this first. Okay, so would it include color work? Because it's an ester. When it's an ester, it ends with H. Before it's, would be really. Well, and so it ends with H acid. And then it goes into H. Yes, on the final compound, what this is, we see that it ends with right, but it starts with what? With A. Is that right, Bob? Is it phenyl methylmalate?
No. Why not?
Before you change it, it's phenyl carboxylic acid. Right?
Well, except that this acid has its own, that is own acid. So benzoic acid, you drop the A acid, make it 8. So benzoate. If you were going to name it the way you were trying to, Taylor, it would be benzene carboxylic acid, not benzene carboxylic acid.
Still feel very iron.
I know. This is the one
It's
that's.
benzoate.
No, that's just the part of the circle. What's on the other side of the ester? A methyl. Is it going to be hyphen or is it space? Exactly. Methyl benzoate.
That's basically. It does space. It's the space.
I looks really similar, right?
Yeah, a little bit.
What's different about I?
It's not very well.
So what's our parent molecule here? It's not the benzoate anymore.
Yeah. So. But it's not a 1000.
It's not an anhydride, it's an ester. Just like H. We just switched which side had the carbonene.
So how would you name just the parent?
Just the part of the circle would be
Like the acid.
or better known as acetic acid.
Yeah.
Ethanoic because it's got 2 carbons, right? So the ethane, drop the E, put oic acid. So you could say, and then if we're going to deprotonate it, it's not ethanoic. I'll write both of them up there because, so if it was, the common name would be acetic acid.
Can't use
So for the esters, just like we did here, you name it like it's the acid, and then you drop the it part in right eight because deprotonated. So ethanoic acid or acetic acid, either way, drop that ending in right eight. Acetate. This is why acetate was one of those polys on bound you had to memorize last year, right? Because it shows up everywhere.
and yet also say the one.
So that's okay. I'm not always 100% convinced I'm saying it correct, so. So either way, ethanoate or acetate, that's our parent molecule, so it's on the other side of the oxygen.
Wait, but in this case, the carbon isn't on the right.
Yes,
Okay.
just like it was here. This included here too.
But like just in the acetate, you know that it has that part.
Correct. Acetate always has two carbons. Good, so it's the same thing. So, what's on the other side of the oxygen, Taylor? Close. With YL, not OL. So phenol. As long as you can spell it, that's okay. And is it space or hyphen? Space. So phenylacetate or phenylethanoate. So for the esters, to recap,
Not done.
find the acid group. That's going to be the side that has the carbonate. That's the part that always tripped me up. For whatever reason, it wasn't presented this way to me when I learned it. And I always had a hard time figuring out which side is the dominant side. The dominant side is the side with the carbonyl. So circle your acid and name it as the acid. Drop the ick and write 8. And then name what's on the other side of the oxygen. With a space.
So it is. Yeah, and then it's acid deeper, piece of beat. Then it's saying what's on other. That's what's on other side.
Bingo.
Get rid of it. It has,
Mhm.
you get rid of it in time. Get rid of the fat. And the acid.
And just because that one uses common name, that's oxalic acid.
We need to know that? Yeah. Exam.
I will try not to use any common names other than the common aromatic ones, like benzoic. Benzoic and acetic, I expect you to know, but there's all like the sulfinic, like and all that, I will not use this. Do any of the math teachers use the 3 lines, the 3 equals? So that mathematically and in sciences means is defined as. So it's not quite the same equal. It's basically the same equals, but it's telling you it's a definition.
Yeah. Yeah. Yes. This is longer than this. It's miss. Yeah. Single pension carbons. Single pension carbons. Carbons with a gas.
Exactly.
Juice. Well, then we have to have a. Like we're pension. I know. Six. Six. How do you know that the federal is attached to the instead of the department?
Because there's a space.
Space. So I know they mean different sides, but like how do you know what side is what? Because
So-
the side that's in the word is what the eight eats the H. Yes, I know, with what's in front of it.
So this is your parent molecule. And this is what's attached to the oxygen. Space is what's telling you, is what's going to delineate between your parent molecule and what's attached to the oxygen.
So
So
like the thing in front is what ends up replacing the H. No, yes, wait.
if we did that, that would be phenyl space 2-phenyl cyclopentane carboxylate. All one word. Because if it's all one word, it's attached to the parent molecule. If it's a separate word, it's attached across the oxygen.
Then this replaces this.
Yes.
Whatever is in front. H.
Yeah.
So eight, like the eight, what's in here should be what replaces the eight. No, what's in there, it's just fun little.
Again,
Because it's all.
they didn't have the foresight to ask you about this for your input when they were doing this. So now we're stuck with what they came up with.
Because whatever's in front, and only if there's space.
Well, and the other way to remember is that the 8 means it's deprotonated, right? It means this was the acid piece.
Right.
This is not part of the acid piece. So everything that was part of the acid piece is all attached to the 8. And the piece that's not part of the acid is a separate word.
It literally ate the eight, it gave itself away, I need to put this, you're saying the same thing over and over.
Yeah, it's okay. We have 2 more. Let's do these other 2 that aren't esters. And then we'll be done for today. They're not 8s. They are amides. Well, the first ones.
Or it would be like. And H two. Then replace that. Yeah, yeah. And then. But y'all have that, do get rid of this. It's acid, we're starting from acid. We're just, and my life has. There we go. I was gonna find it, was hard to remember.
Propionylamide. Again, it would look really, the IUPAC name would actually be propanamide. Looks a little bit more tolerable. But they're similar enough that I barely even consider that a common name. It's basically a different spelling of the IUPAC.
I think for the next one, but it's the same thing.
Same thing.
From the.
The propanoic acid would be the original, so. Draw your propanoic acid. Except it's the chloride version, so you're gonna drop the OH. And replace it with. Chlorine.
Can we have this one that's called for Thursday? Oh, I understand, it's not.
It won't be, it'll be optional. If you wanna do some more practice on this. It won't be until tomorrow, so I've got a full day today. But I'll, as soon as I can, I'll pull out a few more problems like this from the textbook and I'll post them as an announcement on Canvas.
You put the answers, so that I know if I'm doing them right.
Yeah, or we can go over them. Or we'll do them at the beginning of class on Thursday.
Yeah, you have time, that would be great, if we don't today.
I should, except tonight's a board meeting night and I have a baseball game, got lab after this, and I have to write something for academic senate today too, so before my meeting tomorrow. It's a whole, you don't need all that detail. I'll do what I can.